let Z be Gaussian normal, so standardized normal with mean 0, variance 1. We are then defining y to be the absolute value of Z. So y is now folded normal distribution, that's what it's called. And this has been discussed in the book. Now we are asked to find two expressions for the MGF as unsimplified integrals. One based on the PDF of y, so this is not using Lotus, and then one based on the PDF of Z, allowing us to use Lotus. So let's start with PDF of Z. So we are with Lotus. Okay, so this then means that we can just state the definition of the MGF of y, which is the same thing as the expectation of y, and now we're this equality is by definition. This is just by definition of the MGF. This is definition of y. So this gives us the absolute value of Z, like this, and then using Lotus in this third inequality, we can write e to the t absolute value of little z, and now using the PDF of Z, so that's the standardized normal, which is e to z dz, right? So we're fine with just leaving it as an unsimplified integral, as stated in the question. This is well, this is almost as far as we get. We could do a couple of more things to, for example, unpack this absolute value. See, what does it actually mean? It's a little confusing in having it like this. So let's just do one more, which is then saying that, because this is the absolute value, well, what does that mean? It means that Z, this after evaluation, this is always positive. So for all negative Z's, we're making them positive, and all positives just stays as they are. So another way of writing this integral is that from all minus values up to 0, we have e to the minus z t, right? We take all negative values, making them positive, and yeah, let's just copy this part. This is exactly the same, like this, and for all other values, all positive, we just do as we normally do. So I'm duplicating this, putting it here, and then removing the minus sign. That's what the absolute value term states there, and we're just unpacking it to make it look something like we are used to seeing. All right, let's move on to the other part of the question where we're not allowed to use Lotus, but here we would need to, at this stage, we need to use the distribution of y, and we're going to then compare it to the distribution, well, this whole integral here. Okay, so this is a little trickier, so let's find first the PDF. So I'm going to write this as without Lotus, like this. So let's find the first the CDF of y, and then we will take the derivative of it, because by definition the derivative of the CDF is the PDF. So this is now the probability of y being less than equal to a little y. Right, that's just the definition. Now we're going to move to now by definition again, y is, as we said up here, y is this expression here, so we can just change it here, this stage. And now when we make this change, I tend to think about this, that we moved from the y distribution, the y probability, to the z probability, right? So we're now entering a known domain of the PDF, the CDF and the PDF of z, but because we're following this these equalities, we will end up with an expression that utilizes z, because y is obviously a function of what happens in z world. All right, so now what do we do next? Well, at this point we can unpack, and we unpack z as we did. I'm inclined to keep on writing z here. Well, let's just do that so that we keep it absolutely certain what we're doing. So minus y, this is just by definition of the absolute value, right? Now that in turn can be written as right, so we can think about this part here. It's like moving from minus y up to z, and this is from y less than z. So here we can separate out this expression by doing the following. So we have y of p of y, p of z less than y, minus p z up to y. Okay, so how does that compute? Let's think about this visually. So we can think about the PDF of z, right? We're having the mass here. This is 0. Let's imagine now, and this, we have obviously symmetry here. This is, imagine this being y, imagine this being minus y, and what this term is saying is that we want the density in here, right? So what we do then is that what this expression here is doing is saying, okay, so let's take the distribution from, let's take another color. This expression here gives us everything here, but also this piece here. Let's put blue on it, right? And so what we want to remove this piece. So, and this is what this piece is doing. It's taking this away. It's deleting it. Okay. And now, by definition, and we still now in Z world, this is the CDF of Z of Y. It's the CDF minus y. All right, and so this is fine. This is what we usually see. Let's try to switch this around to write it in terms of this. We're going to utilize symmetry here. So that's y minus, and so what is this thing here? Well, let's look at this visual again. So the CDF here of y is the same thing is the same thing if we think about taking everything, the whole PDF, but remove what is here. So instead of moving from here up to there, you can think about the whole thing, but remove this piece here. And that is equal to, so the whole thing is 1, because that's the probability of the whole event happening. It must happen. And then we remove the remainder piece, which is up to y, and we are also adding symmetry here because we are entering from the other direction. Okay, and this now gives us 2y minus 1. Okay, so that's the CDF of y, and the PDF of y. Let's write it like function y. That is the derivative of f of y, CDF of y, which is, because this is standard normal, we know what the PDF is, so that will be then y, like that. Okay, so now we have the PDF, and now we can proceed of calculating this whole expression here at this equality. Instead of using Lotus, we'll use this now, but look that this is actually also using the PDF of the standard normal. Okay, so what we do here next is that we let's copy. Actually, what we do is that we copy this piece here, because this, from here we can move to calculating this expectation, which is, and actually one thing here which is really important is that y is not defined for negative values, so it will not start from 0. The support goes from 0 to plus infinity. Now we can just use e to the t of y, and now the PDF of y is 2, this thing here, which is the normal, standard normal PDF. Okay, and that in turn is, let's keep that standard normal, and then we'll do the following. This is the standard normal, said standard normal. Oh, it's getting super ugly. Like that. Actually, I realize one thing here is that this is going not from minus infinity to 0, it's going from 0 to, my bad, when copying it up. Got that error. And one other thing we're going to do, just to make this equality show very clearly, I'm going to move this down a little bit like this, is that when, right, so look at this, we have 2 here of the same thing, right? So we're going to write this as 2, 0, infinity, e to the t, y, and the PDF, there should be a y here, sorry about that, Right, we have two pieces, and this is awfully similar, not exactly similar, this is exactly similar to this piece over here. So let me just copy this and see if we can make this a quality stick. Is this true? Okay, so what we can do here is that we can, because of symmetry, we can flip minus z to positive z, so we get 0 to z e to the zt z d z plus, and this is the same thing, right? This is the same thing to the zt z dz, and that is in fact the same thing as this expression here. Y and z's are just in a way dummies here, so we can swap y for z and z for y. So we have now by this proven this equality.